Okay, so we'll get started. Thank you guys for the feedback from last Friday. You guys asked a lot of questions about thermodynamics. Since it's a very important topic and the concept that you guys need to understand, so I will go over the thermodynamics again, and hopefully that will address most of the questions that you have raised. But first I would like to continue talking about nuclear chemistry, and then we'll spend part of a Friday lecture talking about effective ionization and how is that useful to us. Here is a list of things I listed out. I know we decided the final will be on June 12th. We have about 3 weeks left for this semester. And if you remember, we spent a lot of time talking about chemical kinetics and how to do the manipulation of math equations. So here are some concepts. You will receive this slide at the end of this lecture, so you don't have to worry about copying stuff down. But it's good to make notes that you find important, because I know there's a lot of information in this class. Okay, so if you guys remember the reaction order and how to write rate law, this will be on the finals, as well as the acid and base. I think that's the most fundamental thing in general chemistry, is to know your acid and base and know how to do those simple calculations, figuring out a pH and understanding what buffer is, because you will encounter that over and over. And also understanding what KSP entails. This is a solubility product. And then another important part, a big part of this class, is understanding thermodynamics. Be able to provide a qualitative description on why reaction happens. Why does the reaction go backward? Why does it go forward? Because this is all we do in chemistry. Think about equilibrium in acid and base, that it's something has to drive the reaction, right? So we'll go back to that in a little bit. And the electrochemistry, unless you go to a very specific class, you probably won't see that again. It's important to cover electrochemistry because we all like to swipe our phone, right? So battery is definitely a very important topic for the next several decades. And then we'll have some previews of advanced chemistry topics. There's not many people working on nuclear chemistry nowadays, but this is definitely a comeback, because this study was originated with the background of World War I and World War II. People want to harvest that huge amount of energy. Then later on, at the end of war, there's no need for the development of nuclear science. But now, because we have more advanced techniques and understanding, and also calculation power, there's slowly a comeback of nuclear sciences. So you can definitely look it up online. There are several nuclear program in the United States and as well as Europe. So if that's something that interests you, I will encourage you guys to look into it. And then also we'll talk about organic and inorganic as an introductory, because these are the main courses for chemistry majors. And hopefully you will find the type of chemistry that you really enjoy. So generally we work on inorganic, organic, physical, analytical, and maybe biochemical. So hopefully you guys can find what you enjoy. So we'll continue with the discussion of nuclear chemistry. Last time, this is just a refreshment of a couple words and definition that we encountered in the last lecture. When we say nucleons are basically protons and neutrons. It describes the chemical property of a specific element. Then we also have nuclei. So basically you can understand it as a type of isotope. It has a fixed number of atomic number and a fixed number of protons and neutrons. We'll get to the stability of these isotopes in a little bit. Isotope, you guys get tested on this concept a lot. Basically, they just have different amount of neutrons that's present while the amount of protons remain the same, and also we know as a Z value. Okay, so we know most of oxygen have molecular weight of 16, but there's some isotope and they are known to be radioactive. The extent of radioactivity is really depending on stability of this. So you can think of it in terms of Gibbs free energy, how willing it is to give off energy to reach to its minimum energy state. When we say radioactive, that describe these nucleus which are not stable and they will decay. So they either emit alpha particle or beta particle, or they have several types of beta decay in the form of high energy electrons. So if you don't understand what that means, I would suggest you guys read the book and you will figure it out, the difference between various mode of decay. So what are radioisotopes? Obviously, just by looking at the word radio, we're talking about radiation, right? So the isotope that emit radiation are called radioisotopes. And this is important because in medicine, we use a lot of radioisotope. Last lecture we mentioned it can use for imaging, and also for those who have cancers, sometimes we use radiation such as gamma ray to treat cancer because it basically destroys the cells. It's a lot of energy. It will cause ionization and the subsequent death of the certain cancerous cells. So let's talk about isotopes. Most known elements, they have at least one isotope, and some will have more than the other. If we think of one main question, what holds these neutrons and protons together? There must be some interaction, otherwise they will fall apart, right? So in physics, there's a branch that studied this, so trying to explain the origin for the stability of these elements that we're working with. But generally, because right now this is general chemistry, we generally think of these elements as a discrete package of protons and neutrons. Somehow they're just hold together, and only under an extreme condition, such as a bombardment of alpha particle and beta particle, and will cause the disintegration of these pure elements. All right, so other isotope, like I said, they will disintegrate or decay, so they become something else. Why do they become something else? Anybody want to give a guess? Why does isotope want to decay? It wants to get to the lower energy state, right? And because it releases energy during this process. And you can start thinking about thermodynamics. What does that mean? You're emitting radiation. It's kind of like the exothermic reaction, right? Or it drives the reaction forward. And also it could be an endothermic reaction if you give your surrounding a lot of entropy. So when we talk about chemical reactions, that could be precipitation. In organic chemistry, there's other reactions between carbon and other elements. That is, they're just forming bonds. So think about the MO theory. We'll get to that in a few weeks. So basically, in chemical reaction, we're dealing with the valence electron. So what is a valence electron? That are the electrons on the outer shell, far away from the nucleus. Because they're far away, the interaction is, or the strength is weaker when the electron is really far away. When the electrons are interacting with each other, what I mean by interacting is you have a probability circle that you're most likely to find an electron, but doesn't mean you will see the electron at a specific spot. So when the bond form, we generally regard it as electron sharing, and we could call this covalent bond. But for nuclear reaction, this is not about the valence electron. For nuclear reaction, it's about what happened at the nucleus. That's why their number of neutron or number of proton or Z number will change in a nuclear reaction. So let's talk about nuclear stability. Generally, so there's a bunch of rules. I don't think I would test you guys on this because it's what people found, okay? There's a trend, but given a guideline, you should be able to use your logic to identify whether an isotope is stable or not. You do not need to memorize all of these, but know how to use these concepts. Given when asked, is this a stable or unstable isotope? So Z83 is the bismuth, okay? But bismuth do have an isotope because, the general chemistry textbook was written a long time ago. But with the research, I think there's a footnote saying that in 2003, someone found a bismuth isotope that has a very, very long half-life. Recall the chemical kinetics section. When we talk about half-lives, that means the amount of the original substance decreased by half, right? So a long half-life, that means it will take a very, very long time to decay. So the stable isotopes, in your book, you will see a chart similar to this, And this is what I found online that I think is more possibility of isotopes. In your book, you will see a straight line and they do a zooming and show that some isotopes that are stable and some aren't. But just by observing this, for the low atomic number, the first 20 of them, this obey to this 1-to-1 neutron to proton ratio pretty well. But this is just by observation. As your Z becomes larger, this line will deviate from the initial hypothesis. When neutron to proton ratio is 1, it is stable. As you can see, as you get to the transition metals, you have a lot of possibilities of different isotopes. For example, tin, it has 10 stable isotopes. Okay, why? It's just the nature of this specific element. So there are some, in nuclear physics, there are some theoretical quantum mechanic calculation that will prove or have suggestion of why these isotopes could be stable. For example, generally the even number will be usually more stable and more isotope. So because one simple way to understand it is you want to have a charge balance. If you have too much of one species, it will be an off-balance system. Okay, and there is also some weird thing, is the magic number. These certain number of isotopes, they are very, very stable. Just like how you get for noble gas, it's just the way it is. For the noble gas, it said 8 electrons in the valence shell is stable, and then the next you go to the higher amount of order. If we remember the electron configuration, because we're dealing with reaction, we only care about the valence electrons. So in the nuclear chemistry, it's a different world, so they have different magic number. And then I want to mention stable isotope. These are the only exception that they are stable, okay? And then also this N over Z value, N is neutron, okay? N over Z value will increase as Z increases, which explain why this is not following this trend, okay? And I want you guys to take a few minutes to observe this graph. Okay, so noting that there's also on the edge, okay, when it's far away from this trend line, your isotope lifetime is very, very short. Although you can observe these intermediate species, right? Because I call that intermediate because this is not what you observe in the end at infinite time. So by experiment, you can really observe this, okay? And then there's a couple that ones that are predicted to exist, and we'll get back to this concept in a little bit when we talk about nuclear transmutation. Okay, so we can also predict the mode of decay that will happen, okay? So if we remember the beta type decay, so that basically changed your atomic number, either by +1 or -1, okay? So when you are neutron rich, because we know we want to offset that difference, right? What I mean by offset that difference is you want to approach N over Z equal to 1 for some elements, right? So when you have too many neutrons, you want to get rid of your proton. And then for the proton rich, will emit a proton out from the system. So just to show, so this is alpha particle, the positron. So when this positron is emitted, your atomic number will decrease by 1. And this is called beta particle. And sometimes there's something called electron capture, but that is not on the product side. That's more of, all right, so for very heavy nuclear, so we go back to the rule, Z is larger than 83, they're generally not stable, okay? And then they will go through alpha decay. So basically you will decrease your atomic number and the amount of neutron that's present by a lot. Okay, and then there's something called decay series. It basically tells you the uranium isotope and this isotope will produce lead in the end. Why is this important? Because in the nuclear reactor, this is the radioisotope that's used. And then this is why I want to become lead, because somehow lead is much more stable to the formation energy of these lead product is much lower. Okay, so you want to get to the lowest energy state. So I'll suggest you guys read the book 1081 and 1082. I know there's a lot of information in this section, but I just want to highlight what I think is important. Okay, so again, how can we apply kinetics? Okay, so we always assume it's a first order, and we can use the half-life calculation. Okay, so there are two ways to monitor the radioactivity. It basically leverages the radiation can cause ionization, and with charge, we can amplify this signal with our electronic circuit, right? So for example, for the ionization counter, that relies on the ionization of argon, and then you can put it into an amplifier, which will give you an amplified signal that you can quantify the amount of radiation that is being given off. So for a figure, if you go to page 1084, if you go to that page, that has a simple setup. Okay, so when the sample decay, okay, it will emit alpha particle or beta particle and whatnot, right? And it can be detected by your detector, okay? So this is physicists built this. So back in the Curie's era, people are very interested in these type of behavior. They're interested in radiation, interested in where this energy come from, okay? So these energy come from the emitted energy, is also called radiation, come from these nuclear reactions, okay? So you're generating new elements, or you can say the element undergo decay, radioactive decay, and becomes some other element. And that extra energy is given off in a form of energy. And then also there is something called scintillation counter. The phosphors, it could be organic and could be inorganic compound, that when they absorb this energy, it will undergo a complicated energy conversion process and later emit out, reflects the absorption of these external energy, and they will re-emit it into a different wavelength, a lower energy photon. You can get that signal and amplify it with your electronic circuit. This is in honor of physicists. So 1 BQ, that is basically 1 decay per second. And in honor of Marie Curie for her work in measuring radioactive and be able to isolate pure radioactive element from or the naturally occurring source for the radioactive compound, generally in the form of oxide. So this is in honor of her. So initially she said 1 Curie is equal to a number of disintegration per second for 1 gram of radium-236. But what does that mean? That means it's 3.7 times 10 to the 10 decay per second. So okay, that's a lot of reaction. But we know from 1 mole, we have a lot of atoms or molecules, right? So let's look at a sample problem, 24.4, which is on 1085, the page next to it. Okay, so just look through this problem. So here in activity, you can think of is how fast this process is happening. That's why I call it activity. And the most important part is watch your unit for such calculation. So if you watch for the unit, you can easily figure out what that number means. So that gives you the physical meaning of these calculations. So one take-home message is that smaller k, that corresponds to longer half-lives, that also refer to the stability. Then if you look at 24.6, so basically someone was able to, this Nobel Prize winner, Professor Libby, was able to quantify how much carbon-14 would be present at each time, right? So we can measure the radioactivity of carbon-14 in your sample to figure out how long this object has been existed for. We know in nature there's a distribution of isotopes, but however, this technique is not very sensitive. Your error range can be hundreds of years. Okay, so carbon-14 can be used to figure out how long this object has been around for. So if you flip to page 1089, this is an assumption that given that the half-life measurement of carbon-14 is correct, okay? This is a timeline of these objects. And if you look at the sample problem 24.6, that shows you the calculation you can do, okay? So you're not required to memorize how to do these calculations, but you should be able to figure out how to solve a problem like this with a simple calculation. Okay, and then you should know what that means by how many disintegration per minute. Disintegration event means alpha or beta particle form, okay? Radioactivity can be quantified as the gamma ray emission. So let's talk about nuclear transmutation. Okay, so where do these elements come from? So we know from high school chemistry, there's 6 elements that are present in abundance in the universe, right? And then for the Earth, it's a little bit different. Okay, so if we think about where all of these things are from, so we can go back to this one form of the alpha particle. You can recognize that it's simply addition in this form. You see the pattern? Okay, so in cosmology, it studies what happened in the outer space. So last time we mentioned about supernova. So we believe that these elements were generated at the very high energy processes. All right, so the first example of knowing that nuclear transmutation is possible is when Rutherford, the guy that used alpha particle to hit a gold foil. If you remember that experiment, the Rutherford gold foil experiment, he was doing the same experiment with aluminum foil. So actually Rutherford found that during his experiment, he was converting the atmospheric nitrogen into oxygen. Basically, and plus alpha particle, and that gave him a proton. One of you asked me whether you need to identify the mode of alpha or beta particle emission. So basically, you just need to understand the balance of your equation. So these numbers has to add up for your stuff on the left and for your stuff on the right, and it doesn't change, doesn't get destroyed. So Rutherford found that, and Irene and Frederick Joy Curie. Irene is daughter of Mary Curie. I think she also won Nobel Prize for discovery of different elements. And then that is her husband, Frederick. They demonstrated synthesis, the first artificial radioisotope, which cannot be found. So she was able to figure out that you have aluminum. It basically accepts an alpha particle, and then you would emit an extra neutron out, but give you this phosphorus isotope. Okay, and then why isotope is important? So in organic chemistry, we have an instrument which I will describe in the later lectures. There's an instrument that we actually utilize these isotopes, and we get different signals. You get different magnetic spin from these isotopes. And then we get the signal, that's what we call nuclear magnetic spectrometer. We can basically use this to figure out our chemical environment. So we can use this technique by looking at the signal coming from the radioisotope, and we can figure out what our molecule look like. Okay, so based on the description of nuclear transmutation, now I want you guys to discuss with your table mate. Is it possible that we can make gold? Just like the alchemists back in the day, before chemistry is a thing, people were just trying to mix things together and trying to make valuable gold. Is that possible? Okay, so if we look at the periodic table, indeed humans are capable of making elements. If you look at these F block elements, so it's possible to make them, but the purpose of alchemy, or the process of making gold from cheap or inexpensive starting material, is that we want to turn something cheap and invaluable into very valuable gold, right? However, such process it will be very energetically intensive, and you will be likely end up with a radioactive gold isotope and decay. Does that make sense? Okay, so now if you go back to your textbook, it has a description. If you look at page 1092, that is the accelerator design. Basically, it can, with the electromagnetic field, you can control these particles, and you can mimic, but not to the full extent of explosion that happen in outer space. Then you can, using these collisions, to induce a nuclear transformation. Now in France, they're also trying to look for the God's particle, right? So in physics, you guys will run into this in more details. So yeah, so these are the modern accelerators. So if you go through this section, you will learn a greater deal of nuclear transmutation. So now we'll move on. So we all recognize this equation, right? E equal to mc squared. Just like chemical reaction, nuclear reaction generate a lot of energy, or you can say not generate, it release a lot of energy in these processes. And radiation, how would you quantify the amount of energy? So we can use this E equal to mc squared to balance such equation, because we know that when a reaction like this happens, the mass decrease. So that extra mass has to go somewhere. Let's look at this sample problem. So the material I use is a little different than the book, but in your book, it's the last section of this chapter. Okay, so for example, if we look at the decay of uranium-238 and to decompose into the 234 element TH, so if we use the equation, okay, we first calculate what's the change of its atomic mass. Okay, so we can calculate this. Okay, so for 1 mole of this substance, it will give you the mass change, right? And we basically times the speed of light square, and that will give you the amount of energy. So that's a lot of energy in 1 mole of such transformation. And then so you can also use a different unit conversion to figure out the energy in electron volts. So remember electrochemistry, we use electron volts. Each electron can carry a certain amount of charge or a certain amount of energy. Okay? And then from that, we can also figure out the ionization potential from such this thing. So that the binding energy, how strongly can an atom or a nucleus hold on to its components. So if we run through the calculation, so spend a minute looking at this example, then you can figure it out the binding energy. Okay, so you can do this calculation over and over for different isotopes and for different elements, and this is what we end up getting. Okay, so now I want you guys to look at figure 2416. So it's on page 1104. Okay, so there's a line that details fusion and fission. So really, the binding energy will dictate which process will happen, okay? So now we'll go into the session of fission and fusion. So if we think of fission, okay, that means a bigger atom, a heavier atom becomes smaller. Fusion, remember fuse means put two things together, okay? So fusion means you combine two elements together and becoming a new element. And in this process, you will generate some extra energy. Okay, so here's the picture. If you're able to generate neutron, right? So you shoot this neutron at a uranium-235 isotope. It will start the nuclear fission process, okay? And we call this a chain reaction. Why? Because one neutron in the end, you end up with 3 neutrons, right? From each of these neutrons will trigger 3 more neutrons from the fission process. So that we call chain reaction. And then also, uranium becomes something smaller, such as this Kr and Ba, okay? And remember the conservation of these neutron and proton, okay? So just this is a mental picture that you should have when you think of fission process. Okay, so here it's just a range of possible reaction that will happen with uranium. So you can see there's a lot of combinations, right? So if you're interested, I'll encourage you to read more about nuclear chemistry, and there's a lot of information online. You can also find very good video on YouTube that will tell you more about these processes. So since you can generate a lot of energy, I would like to read the first paragraph. Because there's a lost mass, right? We just went through the calculation. When you have a mass change, it has to turn into something, okay? It turns into energy, okay? So for 1 kilogram of uranium-235, it can produce 2.5 million times of energy of the same amount of coal. Okay, so that means we can say the energy density of uranium, or in this fission process, is much higher than the combustion process of coal. Okay, and this is why a lot of people want to use nuclear, because it utilizes a very small amount of fuel and generate a lot of energy. Okay, but of course, refining uranium from its natural occurring state, or the uranium ore, and the storage of these radioactive products, because we know when they generate these products, it will still slowly decay, right? And then so that will generate radioactive emission. So here is just a dramatic image to show you what happened at each of these stages. Okay, you can generate element with different atomic number. Okay, so this is something I wanted to show you. So this is what happened. That's why I refer to chain reaction. So the ability to control this fission process, there's a lot of engineering in this. There are certain material that can absorb neutron. Okay, so you can remove the amount of neutron. You can think of it in terms of chemical kinetics. The lower amount of your reagent, the lower concentration, you have less tendency to collide, right? Then if you don't collide, nothing will happen. Okay, so if we don't control the process, that's what you get, right? Atomic bond. I think we are often familiar with this, okay? It's simply several pounds of these material, but of course you have to figure out a way. So this is classified information. What you need to do to make the atomic bomb. Having the uranium is not enough. There's a lot of engineering going into this, but basically you would just create this massive destruction, and the land will remain radioactive for a very long time until these radioactive isotopes become something else or become elements with a very, very long half-life. Okay, so that means the amount of radiation being emitted becomes smaller. Okay, so when I mentioned the material that is boron is capable of absorbing these neutrons, and generally, I mean, this is the design of nuclear power plant will look at. They will insert these control rods into your reactor, and you also have fuel rods. Okay, I don't know the details of how these things actually work, but for a nuclear power plant, basically it relies on, let's go back to here. So basically this huge amount of energy that generated from the nuclear fission process is harvested to boil water, right? So the steam, this expansion of the work, they can drive these turbines so you can generate electricity by turning the wheel. So from a mechanical motion, you would be able to generate currents. So that in electromagnetic class, you will learn more about that. How can you convert mechanical energy into electricity? Okay, so it still rely on steam generators. And again, nuclear plant, I mean, this technology has been around for 20, 30 years. It's a proven technology. but there's also concern of its potential hazard. So I would like you to take a minute to read through this paragraph. What could happen when something goes wrong? So noting that once it went wrong, the internal temperature can be very high, right? And at very, very high temperature, a lot of bad things could happen, right? And then you generate hydrogen, and eventually it exploded. There's nothing you can do. You just have to wait for that thermal energy being released before you can start cleaning up the power plant. So it says it takes about 10 years for the cleanup process. And I know we talk about nuclear fission and how it creates two elements, but it's krypton and xenon, right? And these are gas. So of course, they will just run away. But good thing is they're noble gas, so they cannot go into our life cycles. So this one is also a pretty famous nuclear accident. So it happened in Ukraine, which is next to Russia. Then there basically no life exists in there for a good 20 years. And now it slowly recovers as these radioactive material decay to the extent that the amount of radiation is so small that it doesn't do any damage to living organism. And then more recently, Fukushima power plant, due to the earthquake that is reported in news, and I think you guys know this event, 日本福岛核灾, okay. And then we know that after being irradiated with energy, these energy would still have to be dissipated somehow. Okay, so there's why there's a lot of food safety concern for the crop that is grown in the area that has been exposure to nuclear radiation. Okay, so let's take a break for 10 minutes before we start again. We'll get started. The last topic is nuclear fusion. So when we think about fusion, it's about fusing two elements together. In this process, we can generate helium from hydrogen and with the emission of two neutrons. Okay, so again, simple balances of these things. But however, currently we do not have a way to control such process, and that's why fusion is not being used industrially to produce electricity, even though such reaction would have much more energy compared to the fusion process. Okay, so here's the image that shows the fusion of deuterium with tritium. You can create helium-4, generate a lot of energy. But one problem is here. The very high temperature is necessary to give enough energy, so these elements will actually collide and react, fuse together, because there's also repulsive force when the elements are too close to each other, because that gives the element a reason for its own stability. Is normally they do not react. So only in the presence of very high amount of energy, kinetic energy, they can react. And then the most important fusion process, we can think of the major source of energy from the sun. So we think of in sun and other stars, and there are constant fusion process that's occurring inside. So it continues to give energy to its surrounding. These are all hypotheses, okay? Fusion of hydrogen to form heliums, and because this is what I call a self-sustained chemical process. So the self-sustained chemical process, that means your reaction is producing enough heat to drive the reaction, the subsequent reaction. As I mentioned, you need a very high temperature. So inside the core of the sun, the temperature is estimated to be 14 million Kelvin, so very, very hot. And here is a picture what's going on. They give off a lot of gamma radiation, and I mean, these are all estimation, but if you think about it, it's a lot of material, a lot of substance involved in these processes. And again, we talk about how we convert mass into energy, and there are certain constants that you can derive from E equal to mc squared. So for these hypothetical processes, you can easily estimate how much energy can be produced from these processes. So these are the attempts. People are still trying to figure out a way to control the fusion process so we can actually utilize such huge amount of energy. And also it's regarded as a cleaner energy because it only involves hydrogen and it produces helium that is generally inactive. Okay, so spend a little bit time. For the thermonuclear weapon, this process is possible. But again, like I said, the bomb is an uncontrolled process. Hydrogen bomb, it gives off enough energy that allows it to reach to a very high temperature so you can render the fusion process possible. And like I said, right now people are still building the infrastructure that is required to study such process. So here is the thermonuclear experimental reactor that's currently being built in south of France. And I know it's still 7 years away from this thing being complete. Again, they want to create a very large-scale energy production. And there are some experiments that showing these processes can be done, but it's not a reality yet. So if you find this fascinating, I will encourage you guys to read more about people's effort on fusion process for energy generation. Okay, because we know energy is important and we have increasing demand for cheap energy. Okay, so here I want to show that in a lab that near Berkeley, UC Berkeley, it already generates this amount of energy, which is 1,000 times of power usage of the United States at any given moment. It is an impressive phenomenon, but unfortunately we can't really harvest such energy yet. Okay, I think that is the end for the nuclear session. So I basically highlight the important part you need to know: alpha particle, beta decay, and then you need to know the lost mass can become energy, and you should be able to run these simple calculations. And I think that's all. Then we will start talking about thermodynamics, and hopefully that will answer some of your questions. So let's quickly review different law. The zeros law is basically said at equilibrium, the temperature will be the same among three bodies. The first law, conservation of energy. The second law is stated all real processes occur spontaneous in a direction that increase entropy. I know this is really hard to understand. Some of you may struggle with the concept of entropy. The way I understand entropy is it means disorder or randomness. So just like your table, you have certain amount of items on a table, and its current state is a microstate. Okay? The more items you have, the more types of arrangement that you could have. Then that means over time, according to this law, a real process occurs spontaneous at the direction that increase entropy. So naturally, your table will become messier and messier because you need to do work to actually offset this randomness to make everything organized. You need to put in effort. You need to do work. Okay, so in thermodynamics, it's basically a study of energy. And energy has two forms that we care about in chemistry. One is enthalpy, another one is entropy. So the degree of randomness, a degree of disorder of your system. And of course, if you go into more advanced courses, for example, in physical chemistry, there's another term in the gift-free energy process is the pressure term. When there's a pressure change at a fixed volume, that also does work to the surrounding. If you think of where pressure comes from, why the balloon, when you increase the pressure, when you blow a balloon, it changes shape. Okay, so one of you asked, why do you see this here? I think this is a very vague concept of what exactly is entropy. Why do we need entropy? Because we use entropy to describe the state of a system. Because if there's not enough energy to keep them apart, things won't be the way it is. So we need to put that energy, we need to describe that system. And one example is if you think of the effect of temperature. on how fast a molecule could move. If you think about that, so at higher temperature, it may move faster. At lower temperature, it moves slower, right? Or at absolute 0 K, I mean, that's what the third law said. The perfect crystal will have 0 entropy. Okay, that is an assumption. Entropy is basically just to describe what's going on. So what that temperature is doing to your system. Okay, so one way is we say in a reversible process, you can use this to describe the amount of heat involved over a temperature range can describe this change of entropy. Someone mentioned, okay, so when a system is isothermal or free expansion, why do I see delta S over and over? Now I want you guys to turn to page 900. Okay, so in the figure 20.5 and then figure 20.4, there are two ways to describe entropy. One is to see the change in microstates. We'll talk a little bit more about it in a little bit, or changing heat. So if you look at the figure 20.5, if you think of 1 mole of neon gas in a 1 liter flask, okay, so you can remove the sand. Basically, you need to exert a weight of pressure to keep that system stable, right? As the gas expands, we know the temperature will change, right? So they basically describe the relations and why it has to say reversible, because it minimizes the heat loss to such system that you're observing. So we already mentioned that. I know this is weird when you see, okay, standard state, what exactly is standard state, okay? It's just basically unify all the description to relative to a very standard so that you can say how far off we are from this standard point. Okay, so it provides a reference point to calculate property. So these here, property could be enthalpy, can be entropy. So standard enthalpy change of formation of an element is 0. So that is what is stated. When the people who created this field, they basically have these ground rules so that you can make tables and you can do all the calculations. And also, it could be hypothetical, because for example, we still talk about water vapor at such condition. The standard condition is room temperature, 25 degrees Celsius, right? So at room temperature, 1 atm, water could not exist in its vapor phase, but we still talk about it, okay? So this is just a very hypothetical values to describe different state of system. So some of you asked me what's microstates. If you think about a 4-particle system, at any given time when you observe such system, so this is time 0, when you open up this valve, what could happen? So you have 16 possibility with 4 particles. So microstates is talk about each quantized energy state, but if you think about 10 atoms, then you have over 1,000 ways to arrange 10 atoms. And we know we usually talk about mole of stuff, right? So that is 10 to the 23 atoms per mole. So you have a very, very huge possibility, so many, many microstates. So what are microstates? So we say entropy is a thermodynamic property. Okay, so that's why I asked you to do a lot of calculation involving entropy. And then we know the more microstates you have, the higher entropy is, because if we go back to this equation, here's a Boltzmann constant that talk about we're focused on 1 molecule, right? When you have 1 state, natural log of 1 is equal to 0. Then we talk about how to predict relative entropy. So you think about randomness, disorderedness of your system, okay? So you think about temperature change. Your higher temperature, things move faster, and though in some sense, it will look like things are farther apart from each other. But in some part, they're closer. So really depending on your system. We talk about phase change. I want you to recall the mental image of what's the difference between liquid and solid and gas. When we're generating gas, that means you're increasing entropy. I want you guys to think about dissolution of a solid. For an ionic solid such as sodium chloride, it gains a lot of entropy when it dissolves in water. But how come does the salt will reach to its saturated concentration? Then we have to talk about delta G, okay? What drives, so free energy is a term, it's like basically a currency in the chemistry world to decide whether a reaction that we wrote down is going forward or going backward. So if you want to know how to predict the relative disorderliness, I will refer you to page 902 to 906. So just make a note and go back and spend some time read about it, okay? Next few topics that we're talking about in this class is very irrelevant to non-chemistry major, okay? But I think you should take the time, so the class time give you a designated time that you can start reviewing the concept and start preparing for the finals. In the first slide, I already showed you the important concepts for this class. So you already seen this multiple times, final minus initial, but consider the stoichiometry. Because the law of thermodynamics, if your entropy is larger than 0, that means it become more random. That is favored. It's really hard to predict the sign because there are always exceptions. But if there's a change in the number of mole of gas, we definitely know there's an increase in entropy. So let's talk about equilibrium state. So in acid and base, we talk about equilibrium. We always say, oh, this thing is at equilibrium. Okay, so equilibrium is to describe there's no sub-change in your concentration. Okay, so what drives the equilibrium? It has to do with the fundamental elements of your reaction that you're looking at. So that's why we need to tabulate these tables, because these tables will help us to determine whether a process is spontaneous or not. So recall that heat in Le Chatelier principle, heat is the product, even though it doesn't exist when you write out chemical equation. Someone asked, why would entropy of closed system would eventually increase? I honestly don't know how to answer this because it's really hard to define the question that you asked, but basically the way I would solve this is basically at equilibrium, nothing will change anymore. We will see a table in a little bit. And then when we say a closed system, it basically says no exchange of matter. And then if you do want to see an increase of your entropy, you have to do something to the system, whether putting work or taking away energy from the system. That is how you can change the entropy. Okay, so this is a key table. I don't want you guys to memorize this, but just try to understand this a little bit. You will see this over and over. The most important part is the delta universe has to be larger than 0 for a process to be spontaneous. So what is the system? What is the surrounding? So system plus surrounding give you the universe so that you consider everything. But the system will be that one particular reaction you're looking at. And the surrounding, that has to do with the energy that you give off from your specific system. That's called surrounding. If you flip to page 911, if you look at that figure and try to understand it, if you have a hard time understanding it, discuss with your table mates. I think you can figure out what does that even mean. Why do we consider enthalpy and entropy all together? Then again, the most important equation in this session is Gibbs free energy. So that is what I said, the currency that allow, in the chemistry world, that allow you to do the exchange of matters, okay, to form new compound. You can use this to describe precipitation. For example, in a KSP value, you can use delta G to predict the outcome of chemical system. Okay, so several you wrote down that having hard time confused to the relationship between delta G and these two terms. Okay, this is the master equation. And some of you ask, what's the difference between delta G and delta H? In high school, I know you guys learned that, okay, well, exothermic reaction generally is favored, okay? Why? Because when it gives off heat, it's a negative number. And when it's more negative, that means more heat, it becomes more favorable. For the definition of Gibbs free energy, the more negative delta G, this process will be more favorable. That is because if it already gives off heat, it's exothermic, delta S and delta T is always positive. This delta S term sometimes is much smaller than the delta H term, so you do not need to consider that term. So it's all relative, okay? Then that's why you will get an impression of exothermic process is generally thermodynamic favored. However, you saw last time we did a demo where we mix two solids together, right? And it gets cold. It's an endothermic process, but it's also thermodynamic favored because you observe it in your hand, right? It becomes cold, but the reaction still happens, otherwise it won't be cold. Okay, so to gain that entropy, it needs to take away energy from somewhere. Because we know the conservation of energy, the energy has to come from somewhere, and then the extra energy has to go somewhere. So if you think about the nuclear reaction, you have a mass change and then you just release all that energy. Okay, let's go back. So delta G is the free energy of given stage of a system, and there's also a delta G of formation, and that is referred to the substance. It's about how much energy you need to put in or to create this substance. That basically includes the relationship between enthalpy and entropy. So there's also the delta S of formation for your substance. So you can think about the ice melting process, or you can think about the ice formation. Okay, that you have to account for that delta S. So what's delta G? Just put it in other words, delta G measures the difference between free energy of a reactant product. So again, here is product, final minus initial, product minus reactant. And then big assumption is that they are all at standard state. Okay, so the sign tells us which direction the reaction has to shift to achieve equilibrium. So a good way to understand it, you can write the chemical equation any way you want, right? And we know the reverse reaction is 1 over its equilibrium constant, right? Because it's just a simple math. Which one is considered as a product? Is it a thermodynamically favored product or is it unfavorable product? So then that means it will go to the other direction. Okay, so this is to answer what exactly this delta G is for. And why do we need to calculate the transition temperature that determine whether this is a spontaneous or non-spontaneous process? Okay, so if we look at some simple reaction, okay, in this case, it gives off a lot of heat. So this is a misconception why exothermic processes are regarded as energetically favored. Oh, well, because this is give you a lot of extra energy, okay? It's releasing a lot of energy. And it offset this delta S. But when the temperature is high enough, in theory, you can actually reverse this reaction, okay? This, you can think of this as similar to what we see for fusion, except there's nothing changed in their atomic number, okay? So that's the big distinct difference, okay? And also this conversion of O2 to O3, because you decrease the number of mole of these gas, right? So your entropy is negative. It becomes less disorder. Under normal condition, it's really hard to offset this because if you have a positive number here, you have a negative delta S, so another positive number, your T is positive, there's no chance that your delta G will be negative ever, okay? However, we can still do this reaction through a thermodynamically unfavorable process. We call electrolytic cell, where we put energy in to drive a non-spontaneous reaction. So generally, ozone is produced discharge of oxygen, so you can generate ozone. That is because you put that extra energy to offset the energy difference or meet the energy requirement to make this process favorable, okay? Again, let's look at this one. They're not on par with each other because we're noting the difference in the unit. One is kilojoule and this is in joule. Okay, so only at very extreme temperature above 900 K, you will be able to get a negative delta G. And again, for a system like that, I know this is a very large number, okay? So that means you can set delta G to 0 and figure out these transition temperature, Okay, so these are all relative, okay, and we refer to the table in the back of your book. And this is trying to unify the observation that we see, the behavior, because the chemistry is all about figuring out the patterns. Okay, so again, I know you've seen this before, but I just want to describe it one more time. We can do all the calculation you want, but what does that really mean? Okay, it's not just about looking up an example and reproduce the calculation steps, but it's more important to understand the underlying physical meaning. Okay, so we can look at the vaporization. I mean, this is somewhat related to heat capacity. So we can plug in the standard value, okay? So we know at delta G, it's at 100 degrees, it's 0, okay? So the water can either boil, okay, convert from liquid to gas phase, or can condense from the gas to liquid state. But that really depends on whether you're putting energy in or taking energy away. Okay, but if we think of a system where at 110 degree, okay, this is above the boiling point of water at 1 atm. Okay, so if we run the calculation, again, these are all constant. We change the temperature, the T term, it becomes a negative, okay? So when you evaporate water at 110, or you can think of a system where you superheat the water in a closed system, what will happen? Your pressure will increase, right? As soon as you open up, it will want to reach to the center state, right? It want to be the same as the surrounding. And what drives that process? So you can think of this system as you increase its temperature above its boiling point, but because of a pressure buildup, it prevented from boiling, you're storing that energy. The energy is still present in your system. Okay, so what I mean by the energy is present, it's in order to increase that temperature, okay, you still have to put energy in. So it temporarily stores that energy through the particular system we're talking about. Okay, so 110 delta G is less than 0, it's spontaneous, you just have to remember this. I know this part is very confusing, but if you know how to set up Q and calculation, you can immediately know K is my equilibrium, and then going forward and backward, and in order to satisfy this, and in the context of delta G, and this equation is given. Let's say at equilibrium, that's Q equal to K, so this term will become 0 because at equilibrium it's not going anywhere, okay? It's already at equilibrium. Okay, so where does this equation come from? So if you recall the very initial equation of entropy, S equal to K natural log and the number of microstates, right? So K is the Boltzmann constant, which is the gas constant divided by Avogadro's number. Because in Boltzmann constant, you are concerned about one atom, okay, one molecule. But for Gibbs-free energy in thermodynamics, we use mole, okay? We like to talk about stuff in mole. That means it become R, right? You get that natural log from that initial, because this is statistical mechanics, you try to account for the probability of each state. Okay, so where does this T come from? Okay, I would have to direct you back to the delta G equation, the fundamental delta G equation. And only in that case, we do not consider the term of enthalpic contribution to the system. We only look at the amount of substance that you have in a system. Okay, so that's why we came up with this equation where you can calculate various type equilibrium constant with this equation. And I know a lot of you are confused. Okay, is it really about Kc or Kp? Okay, so I'll come back to this in a little bit. So in our book, if you actually pay attention to the example, they all talk about gas phase reactions, okay? Because that's what thermodynamics like to talk about. In thermodynamics, we care about the expansion of gas and how can that do work for us, right? We care about how increase of entropy can make our reaction thermodynamically favored. So in our book, it is Kp. But in the end, it really doesn't matter what is K, okay? In fact, Ksp is given. You can still calculate about its delta G. Kc is given. You can still calculate the relationship between delta G and your equilibrium constant. So let's go back to this to think about the physical meaning. Okay, so as K become larger, if we plug in this equation, okay, your delta S will become more positive, right? And maximum disorder is good according to the law of thermodynamics. So if the K increase as the delta H become more negative, what it means is the tendency of your system wants to go to lower energy. So remember the gift-free energy of formation? That is exactly related to energy state. So you also see equation where you can calculate the temperature dependence of your equilibrium constant. And then I did mention that example in class, is we can derive such equation from this. This is how the heater reaction is related to equilibrium constant. Okay, so let's talk about coupling of reactions. We talk about ATP and ADP, and we also understand when you have multiple equilibrium, we're talking about transition state. When we're talking about rate law, we're trying to unify all the chemical reaction together so we can use the overall equilibrium constant time equal to K1 times K2 times K3 and so on, right? So that is basically part of this coupling of reaction. So when we say coupling reaction, basically it's talk about a multi-step reaction, and you have rate limiting step, okay? So why is rate limiting? Because it may not be energetically favored. Where does this really come from? So we can think of enthalpy is the final result due to formation of bond and breakage of bond, okay? That's enthalpy. Entropy, how far away of these molecules from each other in a fixed space, okay? And that is related to temperature, because if you increase the temperature, you have higher kinetic energy. So for coupling of reactions, so some step may have positive delta G, that means it's now favorable, but your next step is energetically favorable. So if you satisfy the requirement that your delta G has to be less than 0. Okay, so if you're interested, just read page 920. In real biological system, there are a lot of these coupling of reactions, okay? If you think about enzyme, okay, we know they can catalyze chemical reaction. The binding of enzyme with your substrate, that's a decrease in entropy, right? Because your substrate could be moving around and all of a sudden it's fixed inside your pocket. But however, the overall delta G is negative. That is responsible why chemical reaction could happen within the pocket of an enzyme. Okay, so in our book, we solved entropy of formation in problem 98. So I actually spent some time Google about it. I mean, there's really little I can find, but I think it has to do with the age of this book. Okay, so I found a thermodynamic textbook for engineering. So they actually refer entropy of formation to the entropy that is required to make the reaction happen. Okay, so they refer that to entropy for formation. So if you look at symbol, it's a little bit different, but generally this is the same as our big delta S. Okay, so they run the calculation, and in here it says this CS plus 2H2 gives methane. This is not a real chemical reaction, okay? But we can still, since the way the table is constructed, it still allows us to do some calculation, okay? And then that, in the end, it give you, if we follow the calculation, okay, so this is only 1, and you have 2 of hydrogen, that give you the extra energy or extra entropy from this reaction. Okay, so you can calculate your delta G from this delta H minus T delta S equation and give you the final data. So our book, I think this entropy of formation is basically, initially I understand it as entropy of your reaction. But if you actually go review this whole problem, I think what they really want you to do is this. You only care about how much energy does one substance have. And we know, or how much energy, and this could be enthalpy, contribution, it could be entropy contribution. So in page 914, it states Hess law can be applied. So I think this kind of implies that we can simply do the same thing because this entropy is a state function. So it doesn't matter how you get there, but as long as we only care about the final product, okay? So you can go through a very complicated pathway. So I think for the problem 2098, if you review the whole problem set want you to calculate, I think this is a more reasonable calculation for the entropy of formation. Okay, because otherwise you will be calculating the same thing again. So you basically take the carbon and hydrogen together, it will give you a mixture of product in reality, but you can still apply this and to approximate the energy of formation, or the entropy of formation for your propylene. Okay, so I think that's all we have.